Hey team, this is your second video on water potential, and we are going to discover what it is and how we can use it to predict the movement of water across membranes. Okay, so water potential refers to a measurement that combines the effects of solute concentration and pressure. We've already seen that solute concentration is going to affect where water moves. Okay, water potential also takes into account pressure, right? A push or a pull. So water potential is a value, okay, it's going to be a number that we calculate that tells us how likely water is to move via osmosis. Water will always move from higher water potential to lower water potential. So what does that mean in terms of our water potential value? Well, think about it. If it moves from high to low water potential, okay, a higher water potential means it's more likely to move. Okay, it has more potential to move. So, how do we actually calculate water potential? The formula is water potential, which is this represented by this psi right here. This is a Greek letter. Okay. Pressure potential plus solute potential. That's all it is. And it says this down here too. Okay. We have to calculate pressure potential and solute potential. Normally, you guys will be given pressure potential, but solute potential over here, we are going to calculate today. Okay. So distilled water, so no solute, okay, in an open container, so no pressure, has a water potential of 0. Okay. And this is a pretty high water potential. The more solute you add to a solution, okay, the lower the water potential. So you're decreasing its likelihood to move. Okay. It's almost like you're adding something that's making it heavier, right? It's harder for it to move. And that will be a greater negative number. So again, water will move from areas of higher water potential, which are closer to 0 usually, pure water, to areas of lower water potential. This is osmosis. It's the same thing that we talked about before. It is just using this value of water potential to talk about it. Okay, so on this side of this model that we have here, we have pure water. So the water potential is 0. Okay. Over here, there's some solute. We don't know how to calculate this yet, right? We're just talking conceptual, but we have a 0.1 molar solution, okay? This, if we just looked at this, we would probably remember, oh yeah, water is going to go from high concentration of water to low concentration of water, right? But when we actually get our water potential, it's negative. It's probably not the best way to see that. Negative 0.23, okay? This is telling us, okay, that this is a smaller number than this, so water will move from higher to lower water potential, okay, as we see here too. Great, let's do a little practice with the conceptual. You guys are going to answer these 4 questions in the Edpuzzle. Good. So obviously lower water potential, you guys should have gotten all of the answers with the Edpuzzle, so if you have any questions, we're not going to go over all of these, but make sure that in your Edpuzzle or in your notes, you know any questions that you had from these. Okay. Calculating water potential. So how do we get these numbers? Okay. So each one of these represent a different water potential. So this is distilled water in an open container. Guess what? It has a 0 water potential. Okay. Here, okay, it shows us a plant that's immediately a plant cell immediately after being put into distilled water. Well, the inside of the plant has some solute, so it has a -2 water solute potential, okay, and no pressure. So we're going to have a -2 water potential, right? Which means that water is going to come from outside the cell and go in. Okay. After a while, the plant cell is going to create something called turgor pressure, which we're not going to talk about it. We're not going to have to figure this out necessarily in this unit, but you will be given pressure if it's ever there. Okay. Something to note. Okay. We know this. Pressure potential in an open container is 0. Okay. That's what we see here. So there's no pressure that's acting on this yet. So when calculating water potential, when pressure potential is negligible at 0, we can say that water potential equals the solute potential. So all you have to do is calculate your solute potential, which is what we're going to do today. Okay. So here is the long, fun solute potential formula. So remember, we are calculating water potential without any pressure. Is just calculating solute potential, right? How much solute it has. So the solute potential is equal to negative ICRT, okay? Here are your ICRTs here. Go ahead and fill these into your notes. You should press pause and make sure that you have this table in your notes, okay? Couple things to note. Your ionization constant is usually going to be the same. It's 1 for sucrose, okay? It is 2 for anything that dissociates in water, meaning it's going to actually act like 2 solutes. So NaCl, salt, is an example of that, okay? You'll always be given this, okay? And it's also, they give you all of this on the AP test, which I'll show you in a second. C, okay, is concentration, molar concentration. You'll get this, well, this is referring to the lab that we will do tomorrow, okay? But this is just your molar concentration, okay? Your pressure constant is always the same. It's always 0.0831. I'm having some dyslexia this morning with my numbers. Okay, that number will always be the same, and you'll always be given that number. And then you have to calculate your temperature in Kelvin. They might give it to you in Kelvin, but usually they're going to give it to you in Celsius. Okay, so room temperature is going to be 295 Kelvin normally. Okay, so all you have to do is add 273 to whatever the Celsius is. That'll give you Kelvin. Okay. Great. So this is our, if you need to pause, make sure you get this into your notes. This is what you will be given on the AP exam. Okay, all of this. So they give you all that information. I wanted you guys to get it in your notes so that you have a place for it, right? And so that we're internalizing what these things mean. Okay. They literally also give you what I've already told you as key points. The water potential will be equal to the solute potential of a solution in an open container, since the pressure potential of the solution in an open container is 0. Okay. They also tell you what these are. You will be given all of this on the AP exam. Okay. So I'm going to go through really quickly a model problem. And as I'm doing this, I want you guys to be taking notes. This model problem is also in those guided notes that I had in the handout that should be in your digital notes now. Okay. So we are given an internal environment of 0.5 molar. Okay. It's put in an environment with a sucrose molarity of 0.9 molar. Predict the net movement of water and justify using water potential calculation. So maybe I know what it is just by looking at, I made this drawing here, just by looking at these molar concentrations, but I have to justify using water potential calculation. So I have to calculate water potential. As I said, the first thing I did is I actually drew this out because that helps me visualize what's where, right? Here I have 0.9 is in the outside and then 0.05 here. I can already tell that there's higher concentration of solute here in the environment, okay? So I have to calculate the water potential of both environments. So the internal environment, right, the water potential is equal to solute potential because it's an open container, which is negative ICRT. So what does that look like? We have to actually fill these in. Well, we're dealing with sucrose, so we have 1. Our molarity is here. Our pressure constant is here. And our temperature in Kelvin is here, which gives us a number of negative 1.3 bars. Okay. Now we have to do our external environment. Okay. The beaker solution. Same thing, open container, right? So we are going to have sucrose again. 0.9 molar is my concentration, my pressure constant, and same temperature. Okay. 295 Kelvin. I'm assuming, right, room temperature here at 22 degrees Celsius. Usually they will give you that. So here I get a much more negative number, okay? Negative 22.06 bars, okay? And I actually just put those into my diagram here to make it really clear. I want you guys to write in, where is the water potential greater, inside the cell or in the beaker? Go ahead and record that in the Edpuzzle. Great. It should be on the inside, right? That is a higher number because it is less negative. Okay. This is a much lower number because it is a greater negative. Good. So where is then water going to move? Where is it going to move? I want it, I have here, right, our arrow going out. right? So we're going to go from high to low concentration of water. High to low concentration of water. So I want you guys to practice just writing what is the answer to this question on the Edpuzzle now. Okay, here's your final answer. Net movement of water will be out of the cell from a higher water potential of negative 1.23 bars to the lower water potential outside the cell of negative 22.06 bars. Okay, beautiful. You guys will have a chance to ask any questions right now in the Edpuzzle that you might have. Great. And now I want you guys to try this on your own, and I want you to record your answer in the Edpuzzle so I can see where we're at. You're determining the water potential, okay, of the interior of the dialysis tubing, okay, which is here, and the beaker, and predict the direction in which there will be the net movement of water. Assume room temperature at 295 Kelvin. Go ahead and record or use your notes to work out the answer, and then record your response, your final answer in full sentences in the Edpuzzle. Great. If you guys have any questions after this, please record them in the Edpuzzle. This is the end of this video, and we're going to move on to independent practice next.